Hello, good evening, everybody. I am going to be recording the first video of Unit 4 on periodic trends. Hopefully the first part of this will be a review, and then we'll get into the newer stuff a little bit later. Okay, so as a refresher, the groups are columns in the periodic table, and they dictate the number of electrons in the valence shell. So group 1 has 1 valence electron here, group 2 has 2, and then group 13 has 3, 4, 5, 6, 7, 8, except for helium up here, which has 2 because it only has 2 electrons. So remember, the ability to form cations or anions is dependent upon the number of valence electrons, with the left side of the periodic table wanting to form cations because it's more easy for them to lose those valence electrons, and the right side wants to gain because it's easier for them to gain than to lose. Of course, boron here, group 13, also likes to lose because it only has 3 valence electrons. Group 14, which is the carbon family, it doesn't like to gain or lose. It prefers to share, which is why there are so many different types of carbon-based compounds, because it can form 4 different bonds with things and form a variety of different organic compounds. So here's the group numbers according to IUPAC. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so 3 through 12 are the transition metals, and they have variable group numbers of valence electrons, as we learned last unit, due to the ability to lose from both the D and the S sublevel. So periods in the periodic table are the rows, and this represents the number of energy levels occupied by electrons. So everything in the first row has 1 shell, the second has 2, 3, and 4, so on up until 7. And of course, be careful with the transition metals, which is the D block here, because remember, this row here isn't actually the 4th energy level. It's 3D, so it's actually in the 3rd energy level. So yeah, don't get that confused. So as a reminder, group 1 is called the alkali metals, and group 17 is called the halogens. Remember, they're very reactive because they only need to gain 1 valence electron, just like the alkali metals are very reactive because they only have to lose 1 valence electron. Group 18, the noble gases, which are hoity-toity and happy the way they are, so don't like to gain or lose any valence electrons. We have our transition metals here. Of course, except zinc. Remember, zinc isn't considered a transition metal because it doesn't have any unpaired electrons in the D block. Then we have the rare earth metals, also called the lanthanides or lanthanoids. Then the actinides/actinoids are down here, which are mostly radioactive and pretty much only exist for very short periods of time in a laboratory setting. And then, sorry, this should say metalloids. I don't know why it says actinoids. My bad. So the metalloids are along this stair-step line here. So the green ones represent the metalloids, which have properties of both metals and nonmetals due to the fact they can be brittle, like nonmetals solids are, like phosphorus or sulfur, but they can also conduct electricity somewhat like metals. And I did want to point out astatine here. There is some debate as to whether or not it is considered a metalloid or not. Of course, metals are over here. Anything to the left of the stair step are metals. So after the transition metals, these metals are called post-transition metals. So things like lead and aluminum are post-transition metals. And then the nonmetals are anything right of the stair-step line and the metalloids. So the periodic table is arranged to show that properties repeat periodically. So everything in the same group has the same number of valence electrons, so they will have similar chemical properties. And that's called periodicity. So things like effective nuclear charge, atomic radius, ionic radius, ionization energy, electron affinity, and electronegativity are all trends that demonstrate periodicity due to the number of valence electrons in the group. Okay, so let's look at trends in effective nuclear charge. Okay, so nuclear charge is represented by the number of protons in the nucleus. So of course, as you go from left to right, the atomic number gets bigger, so the nuclear charge is going to get bigger. And nuclear charge also increases down a group because, of course, atoms are getting bigger. There's more protons as you go down the group. But effective nuclear charge is different. Effective nuclear charge is the force experienced by the outermost valence electrons due to the pull from the nucleus. So it depends not only on the size of the nucleus and the number of protons, but also on the number of energy levels in that atom, because the more energy levels between the nucleus and the valence shell, the more shielding those valence electrons will feel. So shielding is kind of like those inner energy levels get in the way of the nucleus pulling on the valence shell. So the more energy levels you have down a group, the shielding will increase. So the effective nuclear charge is actually going to stay the same down a group because yes, the number of protons go up, but the number of energy levels also go up, which means the effective nuclear charge will be the same. However, going across a period, you have the same number of energy levels, because each period is just that energy level. But the number of protons go up. So that pull that those valence electrons feel is going to be stronger. And so that means the effective nuclear charge is going to go up, which is why atomic radius decreases across a period. So speaking of atomic radius, we already know the trends in atomic radius, so you don't have to predict these, but the atomic radius I did want to define is going to be the distance between the nuclei of two identical atoms divided by 2. So if we have two identical atoms right next to each other, half the distance between those two would be considered the atomic radius. It's also known as the distance between the nucleus of one atom and its valence shell, which is here to here, which is the same as the radius. Okay, so that is the definition of atomic radius. So atomic radius is going to decrease across the period because more protons are being added to the same shells. So the shielding doesn't change because we have the electrons being added to the same energy level, but those protons are going to be pulling on those valence electrons more, meaning a greater effective nuclear charge. And so a stronger electrostatic attraction is going to be occurring between the nucleus and the valence electrons. Looking at atomic radius going down, you can see that it gets bigger because of the existence of the additional energy levels. So if you're thinking about the distance between the nucleus and the valence shell, it's obviously going to get bigger the more energy levels you have. And of course, looking at the transition metals, they kind of follow the trend, but there are definitely some that can break the trend, especially looking here at the lanthanides due to the lanthanide contraction that exists in this series. So now let's talk about trends in ionic radius, because we know trends in atomic radius pretty well, but what about ions? Well, cations are positive because they have lost some electrons. So if you remove electrons from the outer shell, right, you no longer have the valence shell being the outer shell. Now the one underneath it is the valence shell. So the atomic radius is actually going to be smaller for cations as opposed to the parent atom. Negative ions, or anions on the other hand, have extra electrons being added to that valence shell. So because of that, they're going to have more repulsion between electrons in that valence shell, which in turn actually makes the nucleus bigger. So anions have bigger atomic radiuses than their parent ion. So if you think about fluorine, fluoride has a bigger, fluoride has a bigger ionic radius than fluorine because it has that extra electron added. So the ionic radius is going to decrease from groups 1 to 14 for cations. So it's still true that the trend is getting smaller as you move from left to right. It's just cations are generally smaller than the parent atom. And then anions are also going to get smaller, going from groups 14 to 17 for anions. Not that group 14 really likes to form anions, but if you made it form an anion. But anyway, it gets smaller because the effective nuclear charge goes up, but generally speaking, a nitride ion is going to be bigger than a nitrogen atom because of the additional electrons added to that atom. Now let's talk about ionization energy. That's the energy needed to remove a mole of electrons from a mole of gaseous atoms. So ionization energy and electron affinity is usually referred to in terms of moles. So we don't usually refer to it in terms of 1 electron for 1 atom. Because we can't really measure that, but we can talk about it in reference to a mole of atoms. So it's the energy needed to remove a mole of electrons from a mole of atoms. And we have different levels of ionization energy, because if you take away 1 electron, that's the first ionization energy. If you take away another, that's the second ionization energy. So the first ionization energy, like I said before, is going to be the energy needed to remove a mole of the first mole of electrons from a mole of atoms. So the first ionization energy for sodium is going to be Na goes to Na plus an electron, right? Because it lost an electron. So the trend across period 3. So let's look at this trend in ionization energy. So you can see here, the ionization energy typically goes up as you move across a period, which is typical. We said that before because, you know, the smaller the atom, the harder it's going to be to pull away those electrons, right? But there are variations in this trend. You can see we have a slight dip from magnesium to aluminum and from phosphorus to sulfur. You don't have to explain these variations unless you're choosing to go along the HL route. I will include this explanation at the end of the presentation for those that are thinking about going into HL. But if you're just planning to stay in SL, you do not have to explain these little variations in the ionization energy trend. Looking graphically at atomic radius, you can see group 2 elements. So going down a group, we have more energy levels being added. So it's typical that you see the atomic radius go up as you go down a group. And the distance is normally measured in picometers because an atom is on the scale of 10 to the negative 12th meters. So we're going to look at atomic radius versus ionic radius really quick so I can show you. You can see here that lithium ions are smaller than lithium atoms, you know, or metal atoms in general are smaller. Metal atoms in general are bigger than their cations, and that's because we are taking away electrons and removing the distance from the nucleus to the outermost shell. So ionization energies are going to decrease down a group, and we can show that here graphically. Looking at the energy, which is measured in kilojoules per mole. So you can see down group 2 going from beryllium to radium, you can see a decrease in the ionization energy. And this is because there are more energy levels as you go down a group, so there's going to be more shielding in addition to the larger atomic radius. So therefore, these are going to be more reactive going down a group because less energy is needed to remove the electron. Metals are more reactive when they're easier to lose electrons. So now moving on to electron affinity. So electron affinity is going to be the energy released when 1 mole of gaseous atoms acquire an electron to form 1 mole of gaseous ions. Just like ionization energy, there can be the first electron affinity and the second electron affinity and so on. But it's more easily visualized in terms of an equation here. So basically what you see here is you have some type of atom, X, represented by X here, and it is a gas. Remember, the definition is going to be 1 mole of gaseous ions. Same thing for ionization energy, it's gaseous. An electron is added to form an anion. That is the equation for electron affinity. Ionization energy is just the opposite, right? You have you would have the X be a plus right here, and then the electron be on this side because it's losing an electron. First electron affinities have negative values, and by convention the negative sign is there because it is showing a release of energy. Whenever an electron is added to an atom that wants an electron, right, such as an anion like fluorine to fluoride, for example, it is more stable that way. So if it's more stable, it is going to release that extra energy, and therefore the electron affinity is going to be represented by a negative number. So electronegativity. Similar to ionization energy, this is the power of an atom to pull an electron towards itself. It's measured a little bit differently than ionization energy and electron affinity in the fact that it is represented using electron volts. Now, you guys have seen electron volts before. There's a conversion between electron volts and joules, like it's a simple conversion. But in your data booklet, it's usually represented as electron volts. So chlorine is going to attract more electrons more than sodium because it wants to form an anion. So it's going to have a very high electronegativity, whereas sodium will have a very low electronegativity. So the most electronegative element is going to be fluorine. That's because it really wants that extra electron because it is in group 17, so it has 7 valence electrons. And it also is the smallest in that group, so it's going to have the greatest pull on those valence electrons from the nucleus. So it is the most electronegative. Then the least electronegative is going to be on the bottom left of the periodic table, and I believe that's cesium. Gotta pull out my pocket periodic table somewhere. I don't feel like finding it right now. But I think it's cesium on the bottom left, and that is because it is very large, right? So it's going to lose an electron really easily, and it's got a lot of shielding. And it's got a very weak effective nuclear charge. So when atoms form bonds, covalent bonds, for example, electronegativity plays a very large role because if the electrons are shared equally, they form what's called a nonpolar covalent bond, and that's because both atoms have the same electronegativity, so one doesn't want the electron more than the other. But on the other hand, if something like hydrogen and chlorine form a bond to form, hydrochloric acid or hydrogen chloride, chlorine has a lot higher electronegativity, so the electron is going to spend more time around chlorine than hydrogen, which is what gives that chlorine a partial negative charge. And I was talking about the electronegativity values in your data booklet. So this is called the Pauling scale, which is the measurement of electronegativity in electron volts. So you can see this trends in electronegativity. It increases going across and decreases going down, and that again is due to the nuclear charge increasing going across and shielding increasing going down, which inhibits the ability of that nucleus to like pull on that electron. So electronegativity is going to go down, going down a group. And the difference in electronegativity is what actually defines polarity, like I said, of these bonds. And I did want to say that this is a continuum. There's not one hard set and fast difference that's going to say you're an ionic bond and you're a covalent bond. But I did want to say that the more ionic character a bond has, then the more likely this is going to be an ionic bond. So the greater the electronegativity difference, the more ionic the bond will be. We've already talked about metallic character. So metals like to lose electrons easily. So of course, going down a group on the left side means metallic character is going to increase. It's more likely to act like a metal if it's easier to lose an electron, which the left side of the periodic table has. The metallic character is going to decrease going across because, of course, as you go across, the atomic radius gets smaller, the effective nuclear charge gets bigger, the nuclear charge gets bigger, and so it's not as easy to lose an electron as you go across the periodic table. So how readily they lose their valence electrons is what determines the chemical properties of those metals. However, the physical properties, such as, their luster, their shininess, their density, their thermal conductivity, that depends on other things. So the malleability and the ductility has to do with the fact that electrons are mobile in metals, so they like to be shared amongst the atoms. So their high density has to deal with the fact that those electrostatic attractions between those mobile electrons and the resulting cations are quite strong, so it makes them dense. And their shininess also has to do with the mobile electrons. So physical properties are more to do with intermolecular forces and the movement of electrons between those atoms, whereas the chemical properties result from how easily electrons are lost. So you guys can practice this by summarizing these trends of atomic radius, ionic radius, electronegativity, ionization energy, metallic character across periods and down groups. And here is a summary picture here to help show you the trends that we've talked about. Oh my gosh, and this is hilarious. So if you want to watch that video, go ahead. It is hilarious seeing the reactivity of alkali metals, but we're going to stop here. Sorry for the length of this video. There was kind of a lot of review and new stuff to cram in here. All right, I'll see you in class tomorrow. Bye.